Okay, so the last part on discussing about integral domains is the concept of a unique factorization domain, right? This is typically the last part left yet. In the previous two lectures, we have talked about Euclidean domains and principal ideal domains. So we'll end our discussion on the important types of integral domains by this lecture, in which we are going to discuss the unique factorization domain. And in the first lecture on these special types of integral domains, the motivation behind starting this discussion was that we want to generalize the important aspects of integers, right? So in case of in case of Euclidean domains, we had seen that we want to ensure a proper division, the concept of a division in an arbitrary ring, as we can see in case of integers, right? Then in case of principal ideal domains, we had also seen the fact that, like in the case of the ring of integers, we have every ideal to be a principal ideal, and we try to generalize that to an arbitrary ring, or specifically an arbitrary integral domain. And now what we want to do is that we want to have a generalization of the fundamental theorem of arithmetic. So I can also think of the concept of a unique factorization domain as an integral domain which ensures the fundamental theorem of arithmetic. So what was the fundamental theorem of arithmetic? That is, provided any integer, I can express it as a product of primes uniquely. That's typically the fundamental theorem of arithmetic. It will be more obvious if I restrict an integer to positive integer. So provided a positive integer, I can talk about a product of I can talk about expressing it as a product of primes uniquely. If I have a negative integer, then still I can do the same thing with just a multiple of -1, right? For example, if I start with an element, let's say 15, I can write it as 3 times 5, and in other words, if I have -15, then it's just -1 times 3 times 5. So I can still express -15, a negative integer, as a product of primes with just an additional multiple of -1. So this is what we want to extend to an arbitrary ring in this case, and this ring in which such a factorization is possible is what we call a unique factorization domain. So to dive deep into unique factorization domain, let us first fix some definitions, which are also quite obvious. Some of these definitions are already seen. So definitions. So this is just for completeness. That is, since we are talking about a topic independently, though I'll use some concepts which I have previously covered, but still it's better to provide some definitions which are only important ones, which are quite relevant. For example, we already know what is meant by an element dividing another element, right? So I already know this concept, that what is meant by B dividing A, right? That is B dividing A, or in my terms, I was calling it to be properly dividing A. So it was basically so this is basically meaning that there exists some Q in R, where R is a integral domain. I'm not specifying that anymore, such that I can write A as B times Q. Okay, but this concept of properly dividing, this will get a bit altered in this lecture. So let me precisely give a definition of what I want to discuss now. Okay, so let me just rub this out and let me start afresh. Okay, so yeah, so we say that B divides A in R. So R is an integral domain if there exists some element Q in R such that I can write A as B times Q. Okay. The second definition it's quite important, is that from 1 from 1, so I can say that B is a divisor of A, and equivalently I can also say that Q is a divisor of A as well. So I can, if I can extend the what I said in point 1 is to be from 1, B is said to be a proper divisor. So B is said to be a proper divisor of A if neither B nor A is a unit, not Q is a unit. If neither B nor Q is a unit, nor Q is a unit. Okay, clear? Number 3 is that we say an element is irreducible in R if it has no proper divisor. Okay, an element A in R is said to be irreducible, if A has no proper divisor. That is, whenever we get a divisor in R. So whenever we get a divisor of A, either the divisor is itself a unit or the quotient is a unit. Okay. Number 4, that let A and B be in R. We say that A is an associate. This is said to be associate. A is an associate of B, or B is an associate of A, if and only if A can be written as U times B, where U is a unit. Now obviously, see, we can write A as a unit times itself. That's quite obvious, right? I can write A to be 1 times A. If I have A to be equals to UB, then I can just put the inverse of U on both sides, and I can write U to be B to be a unit times A, right? Moreover, if I have A is equals to UB and B is equals to UC, so let me just precisely make this observation, that if I write A to be UB and I write B to be U dash C, then that means A can be written as U dash C, but U and U dash both are units, so their product is also a unit, right? So what I exactly want to claim here is that the relation of being an associate is basically an equivalent relation. Okay, and hence just calling a pair of elements to be associate is enough. We do not need to specify a direction, that is whether A is associate to B or B is associate to A whatsoever. We can just say that these a pair of elements is associate if and only if we can write either of them as a unit of the other, as a unit times the other. Okay. Now, so this will actually help us in discussing what I actually want to do in this lecture. Now see, these are some trivial observations which I am not mentioning yet, but you can easily observe that if A and B are associates, so this will be the symbol I will essentially use for claiming to be associates. So A and B are associates if and only if the principal ideal generated by A is same as the principal ideal generated by B, right? Because if A is a unit multiple of B and B is a unit multiple of A, then this precisely holds from either side. Okay, you can justify this. This is just a very simple observation. It's a one-liner observation. Moreover, in terms of ideals, we can also talk about irreducibility in this way, that A is irreducible if and only if, first of all, A is a non-unit, so the ideal generated by A is not the whole ring, and A is contained in the ideal generated by 1, that is A is a proper ideal of the whole ring, and there does not exist a principal ideal, say C, such that A is properly contained in C and C is properly contained in the ideal generated by 1, because if that happens then C will work as a proper divisor of A, but we are claiming A is irreducible. So this is a very obvious observation. Okay. Now the first thing which is quite important to observe here is that, or rather is quite an important observation, which actually gives a correlation between two important types of elements in a ring. Like previously we have encountered an element which is called a nilpotent element, right? When we were discussing our radicals, we had observed that what is the concept of a nilpotent element. There are two more important elements when we are talking about rings, which are called the prime elements and the irreducible elements. So irreducible elements is what we have already defined. Prime elements are the ones whose the generated principal ideals are prime ideals. So definition: an element A in R is prime if the ideal generated by A is a prime ideal. Okay, clear? Now this definition you can also relate it to what we discussed in case of integers, right? The important fact is that if you consider the ring of integers, then any prime element you take, you will find that it's a irreducible element as well, right? Because if you observe that in case of integers, what are the only units? The units are 1 and minus 1, right? The units are 1 and minus 1. So any prime you choose, you can write the prime is typically irreducible because it has no proper divisor. The only divisors of a prime is the prime itself and the unit 1, right? So this is quite relatable to what we have seen in case of integers. Moreover, if you talk about the polynomial rings, let's say, there you will also see, if you consider the the elementary division of polynomials which you have seen in your junior classes, you will also see that if you consider a polynomial which is irreducible, that you cannot reduce it to any polynomial which is of lower degree, or you cannot divide it down to a polynomial of lower degree, then the ideal generated by that polynomial will also be a prime ideal. That's a quite easy observation. So therefore there is a correspondence between prime elements and irreducible elements in case of the ring of integers and the ring of polynomials, provided the ring of polynomials is the coefficients coming from a field. Precisely, if I talk about the coefficients coming from a field, that is, if I talk about Z and if I talk about the polynomial ring fx, where f is a field, that's what I am trying to discuss here. Okay. Now a very elementary observation is what you can observe is, let's say you choose a prime element. Okay, let A be in R, R is an integral domain, and let's say A is a non-zero element, so B irreducible, or let's say it is prime, okay. So this implies that the ideal generated by A is a prime ideal, Now let A B is equals to B into C. So we are dividing A by B or C, whatever. This will imply that BC is coming inside the ideal generated by A, but this means that I can write BC as, or since A is a prime ideal, I can say that B is in A or C is in A. Okay. Without loss of generality, let B be in A. Now if B is in A, then this means that I can write B as, say, A times D, where D is some element from capital R, but then I can put this in this equation, I can put this here. So if I put this here, I will get A to B A D C, which implies A times 1 minus DC is equals to 0, but this is an integral domain, so I can talk about a cancellation, which I could also talk about directly from here, or which means that 1 minus DC is equals to 0, or which implies DC is equals to 1. but this implies C is a unit. This implies C is a unit. So if C is a unit, that specifically claims the fact that A has no proper divisors. In other words, A is irreducible. This implies A is irreducible. Thus, in any integral domain, prime elements are irreducible. So we have actually proved a proposition which says that let R be an integral domain, and let us choose a non-zero element from R such that A is prime. Then A is irreducible in R. Clear? But can we say about the converse? That's my question. So on a general note, this is not true. That is, I cannot say that any irreducible element is a prime element in any arbitrary integral domain. And till now you have seen that most of the counter examples are coming from the quadratic ring of integers. So eventually it will follow the same here as well. If I choose the quadratic ring of integers, say z root minus 3, and I choose the element 2 out of it, then observe that suppose I write 2 as say a plus b root minus 3 times c plus d root minus 3, then I can write the conjugate of 2 as a minus b root minus 3 times c minus d root minus 3, but this will say that 4 is equals to a square plus 3b square and times c square plus 3d square, right? So this implies that a square plus 3b square divides 4, which means that a square plus 3b square can be 1, 2 or 4. Okay. Now observe that a square plus 3b square can never be equal to 2, right? Now a square plus 3b square can never be equals to 2. Okay, for any integer a and b, it can never be equal to 2. Therefore, the only possibilities are whether it's 1 or 4. Okay. Suppose it is 4. So if it is 1, then the observation is trivial, which you will eventually see in this case as well. Suppose a square plus 3b square is 4. Then this will mean that c square plus 3d square is 1. But this will eventually mean that c plus, so eventually what I will get is that c is, so this part should be 0, right? Yeah, this part should be 0. So c must be equals to plus minus 1, right? Or c plus d root minus 3 must be equals to 1, for example. Sorry, c plus d root minus 3, right? C plus d root minus 3. So c plus d root minus 3 is equals to 1, right? But this is a unit, which is a unit, which is a unit. 1 is basically 1 plus 0 times root minus 3. So it's basically a unit. And the same will follow if I choose a square plus 3b square to be 1. It will follow the same. So what we eventually see is that the element 2 has no proper divisor. So this implies 2 is irreducible. 2 is irreducible. But is 2 prime? That's the question I should ask. If you observe that, I can write 2 as 1 plus root minus 3 times 1 minus root minus 3, right? Isn't this the fact? I guess it is, right? Yeah, it will follow up to be 2, right? Just complex division, right? So this eventually implies that so this must be in the ideal generated by 2, correct? This must be in the ideal generated by 2, but but either of the elements are not in the ideal generated by 2, right? Sorry, I'm doing a grievous mistake here. I'm very sorry. I'm extremely sorry. 1 plus root minus 3 times 1 minus root minus 3, this will be equals to 4. Yeah, correct. I'm extremely sorry. This is inside the ideal generated by 2, which will eventually mean, now if 2 is a, if the ideal generated by 2 was prime, then either of the elements must be inside 2, which is not possible, right? But either of the elements are not in the ideal generated by 2, which implies 2 is not a prime, because the ideal generated by 2 is not a prime ideal. Okay, clear? Okay. But to ensure that now this is an obvious step which we should take to ensure that there is some integral domain in which we can bijectively talk about or equivalently talk about irreducibles and primes, and that's one more a reason why the unique factorization domains have come into existence, right, or have come into discussion. Because if you talk about a unique factorization domain, then we can talk about equivalent correspondence between irreducible elements and primes. Okay. So now let me precisely give the definition of unique factorization domains. So an integral domain R is said to be a UFD, that is a unique factorization domain, if every non-zero element of R can be expressed as a product of irreducibles uniquely up to associates, or often use the term uniquely up to a multiple of a unit. Okay, so expresses a product of irreducible, you can also add this, up to a multiple of a unit. Okay. So this is the precise definition of what a unique factorization domain is. So what I'm trying to say here is that if I choose an element A from R, then I can write A as P1, P2 till Pn, where each Pi is irreducible, and if I equal it to say Q1, Q2 times Qm, which is another factorization, then this implies that n must be equals to m and Pi must be an associate of Qj for all I and j. Okay. This is the more or less exact visualization or the mathematical expression for what a unique factorization domain deals with. Clear? Okay. Now the observation which is quite trivially coming out from here is that Zi is a unique factorization domain, which will be more clear if I claim that there is a inclusion of Euclidean domains into principal ideal domains, which we have already established into previous lectures. But then principal ideal domains also get included into unique factorization domains. That is, if you start with a principal ideal domain, then that will eventually become a unique factorization domain as well. We'll prove this in this lecture. That's the most important proposition, or the central theorem, you might say, of this very lecture. But you can easily observe that if I talk about Zi, and let's say I choose the element, let's say 5, then I can write 5 as 2 plus I into 2 minus I, and I can also write it as 1 plus 2I times 1 minus 2I. But you can observe that 2 plus I is basically I times 1 minus 2I, and 2 minus I is I times 1 plus 2I, right? So you'll get isn't it, or I should add minus I, correct, minus I times 1 plus 2I. Got it? Clear? Okay. So Now I and minus I are units in Zi, right? Because their norm is, so if you recall that in a quadratic in a quadratic ring of integers, there we have defined a norm, and with respect to the norm we had said that if you have a unit, then the norm of that unit must be plus or minus 1. What should the norm of I? So it's I times the conjugate of I, so it's precisely 1, right? And same you can talk about minus I as well, right? So I and minus I are units in Zi. So precisely this implies that 2 plus I is an associate of 1 minus 2I, and 2 minus I is an associate of 1 plus 2I. Clear? Okay. So somewhat it's clear that Zi is a unique factorization domain, but what's more important is the motivation behind defining a unique factorization domain is that we can equivalently talk about irreducibles and primes. So proposition: in a UFD, irreducibles are primes. Okay. The proof is actually quite simple. See, there is no point of talking about a unit element. Okay, it's better if we talk about a non-unit element. Okay, otherwise if I talk about a unique element and I proceed to form an ideal with respect to that element, I'll get the whole ring. So it's better if I talk about a non-unit element. Okay, what I try to do is that I'll choose out an element, an arbitrary element which is irreducible from R, and then I'll show that the ideal generated by that element is a prime ideal. Okay. What we do is that we choose a non-zero irreducible element from R, let's say A, then show that the ideal generated by A is a prime ideal. This will give us our observation. Okay, so let's prove it. So what will we do is we will take a product of elements in the ideal and we will show that either of them is in this ideal. Okay, but this implies that I can write BC as AD, where D is some element from R. Now B, C and D, all these elements are coming from a unique factorization domain, so they will obviously have a factorization into irreducibles, which is unique up to associates. So I can write B as, let's say, B1, B2 till say BR. I can write C as, let's say, C1, C2 till say CS, and I can write D as, let's say, D1, D2 till DT, where each BI, CI, DI are irreducibles. But we know that this expression is unique up to associates, right? So the right hand elements individually must be associates to left hand elements with arbitrary indexing. I am not talking about corresponding elements being associates. That I am not talking about. Suppose I have a factorization of P1 till Pn and another factorization of Q1 till Qm. I am not really talking about P1 being an associate of Q1. I am talking about some Pi is associated to some Qj. So in this case, I will have some element from the right hand side to be an associate to some element of the left hand side. This will happen for each and every element. In other words, this implies that A is an associate to some Bi, or A is an associate to some Cj for some I and J. For some I and J. Okay. But if A is an associate of Bi, this means that A is some unit multiple of Bi, or in other words, A divides B, right? So in other way, A is an associate of Bi means that I can write Bi as a unit multiple of A, or A divides Bi may not be a proper division, but A divides Bi, right? But if A divides Bi, that typically means that A divides B. So this implies that A divides B, and in this case we will equivalently have A divides C, But if A divides B, that means that B is in the ideal generated by A, and in this case we have C in the ideal generated by A, which eventually means that A is a prime ideal. A is a prime ideal, which means that A is a prime element. A is a prime. Clear? So, in case of a unique factorization domain, we can equivalently talk about prime ideals or prime elements or reducible elements. Clear? Now, one thing which I should have mentioned while defining a unique factorization domain, which I guess I have missed out, which is this factorization is unique. Sorry, it's finite. Let me go back to the definition. Sorry, where did I define the unique factorization domains? Yeah. So, can be expressed finitely. Can be expressed finitely as a product of irreducibles. So, there is a finite factorization, which is itself what we have seen in case of integers, right? There is a finite factorization. Now, how can we ensure or how can we get hold of this factorization? That is quite an important observation to have in hand. That is, suppose R is a UFD and I choose an arbitrary element from R, obviously non-zero element, let 0 not equal to A coming from R. Now, if A is a unit, then there is nothing to talk about a factorization, right? Then it is trivial, right? So let A be a non-unit. Let A be a non-unit. Sorry, I guess I have stated a wrong statement. If A is irreducible, then there is trivial, right? If A is irreducible, then it's trivial. There is nothing to talk about if it is reducible. Okay. And we need the concept of it being a non-unit, because otherwise it's also trivial case, right? So let me just take it to be in the assumption only. So let 0 be in R, be non-unit, be a non-unit. Okay. Clear? Let A be a, so this is no more needed. Let A be irreducible. Let A be not irreducible. Sorry, let A be not irreducible. Okay. Then if A is not irreducible, then it has proper divisors, right? This implies A has proper divisors. So if A has proper divisors, this means I can write A to be B times C, let's say, where B and C are non-units, right? Where B and C are non-units. So if B and C are non-units, so suppose B and C are irreducibles, then again we are done, right? Then we are done. Okay. If not, then we can further take hold of the proper divisors of the reducible element. Then we can take hold of the proper divisors of the reducible element, which is the opposite of being not irreducible, I mean synonymous to being not irreducible, proper divisors of the reducible element, and proceed the factorization. Clear? So in this way we can continue a factorization. And now the problem is that when can we be sure that this factorization or this process, it terminates finitely? Because I can actually get hold of some rings, some integral domains, in which this factorization can continue infinitely long. For example, if I choose a polynomial ring, let's say, one second, let's say I choose a field K, or let's say I choose a field F, and I choose this polynomial ring. F is a field. Now what we do is that we take hold of all the 2 to the power kth roots of x1. Consider, let's say, xi to be the 2 to the power kth root of x1. Okay. So x1 is 2 to the power 0th root, x2 is 2 to the power 1th root, and so on and so forth in that way. So that is, let's say, x2. So basically what we have is x2 squared is x1, x3 squared is x2, and so on. Okay. We take R to be the polynomial ring with the variables of as these x1, x2, and it continues, right? Then in this ring we'll have infinite factorization. And why do we have infinite factorization is that, so the reason is quite precise, we will be eventually proving, which is that this ring will have an infinite increasing chain of principal ideals. Okay, this ring will have an infinite increasing chain of principal ideals, and that will say that this element x1, precisely this element x1, will have a infinite factorization. But why is this observation necessary? Now this can be trivially justified, because every time you get hold of a proper divisor, suppose let's say let B is a proper divisor of A, then this means that the ideal generated by A is strictly included in the ideal generated by B, and the more proper divisors you get, the more strict inclusions of principal ideals you get. Okay. So if this increasing chain of principal ideals, it gets terminated finitely, then the point it gets terminated, we are left with a factorization of A which abides by the definition of a unique factorization domain in some sort. Or even if I not talk about factorization in terms of irreducible, this factorization is by far finite. That's more important of a concept which we now want to discuss. Okay, and this is something which actually ensures a finite factorization, as I just said. So I can just express this as a proposition. Which I can actually say for any arbitrary integral domain. So let R be an integral domain, then the following are equivalent. I am not going to prove this, but I guess whatever I said, you can just fill in the gaps and just write it down rigorously. That or even we don't require this as a proposition, because eventually when we are gonna prove the central theorem, we will get hold of what I am trying to say here. And I guess it's now enough discussion before we move on to the central theorem. So the central theorem, this will consider what I am trying to say, central theorem. So let me just speak in words of what observation I previously spoke about. What I am trying to say is that if we are in an integral domain and we choose a non-zero non-unit element from that integral domain, then the element will have a finite factorization into irreducible elements of that integral domain if and only if there exists no infinite increasing chain of principal ideals in that very integral domain. That's what I exactly meant, and we can actually extend this, or in fact include this in our central theorem, which will obviously get included as well once you see the proof of it. So central theorem is typically saying that theorem, every principal ideal domain is a unique factorization domain. In other words, we have proved that a Euclidean domain implies a principal ideal domain, which eventually implies a unique factorization domains. So typically what we are having is that, so if we start with a Euclidean domain, then we will land into a principal ideal domain, and then we will land into a unique factorization domain, and all these are inside some integral domain, right? Now all integral domains are not fields, right, but all fields are integral domains. Yeah, we can extend this chart anytime, but I guess this is by far most precise with the discussions we are having from the previous two lectures. Okay, clear? So let us prove this theorem, and the proof is actually very simple, but it's quite lengthy because it's a bit conceptual. The proof. So what we start with a non-zero non-unit element of R. So R is the PID we are talking about. So if R is the PID, so let 0 not equal to A be in R, be a non-unit. Be a non-unit. Okay. Now if A is irreducible, we are done. Else write A as A1 A2 with A1 A2 being non-units. Then if A1 A2 are irreducibles, we are done. Else we proceed similarly. Okay, that is, if one of A1 A2, let's say A1 is not irreducible, then I can write A1 as, let's say, B1 times B2, which are non-units. So A eventually becomes B1 B2 A2. But again, if B1 B2 A2 all the three, so A2 is by assumption is at this moment irreducible. So if B1 and B2 are both irreducible, then we get a factorization of A. Otherwise, if one of B1 or B2, let's say B2 is not irreducible, then we can again get proper divisors of B2 and include that in the factorization of A. So this process will give you the factorization of A, but we are concerned about the fact that this factorization must be finite. So to show that this factorization is finite, we must show that there is no infinite increasing chain of principal ideals in R. Okay. So let's do that, and that will eventually give us what we exactly want. Okay. Suppose I1 strictly contained in I2, strictly contained in I3. This is an infinite chain, strictly contained in R. So these are all in giving you the chains. There are infinitely many ideals in this inclusion. Is an infinite chain of ideals in R. Okay, properly contained ideals in R. We are to show, so if I want to show that there is no infinite increasing chain, then I must show that this chain, it must terminate at some finite point. So we are to show that there exists some n, some natural number n, such that Ik will be equals to In for all k greater than equals to n. That is, once we cross the point, cross the ideal In, every other ideal which perfectly which contains In are all should be equal to In. So this typically means that this increasing chain must stabilize at some point. This will eventually show that there is no infinite increasing chain of ideals in R, which eventually gives us a finite factorization of the elements in R, which was exactly the discussion which we had shown in the, which we had discussed in the, before just discussing this theorem. Okay. So how do we prove this? Okay. Now, so we consider the union of these ideas. Let's say I is the union of these ideals. Okay. So I is equals to 1 to infinity. Okay. Now clearly I is an ideal. Clearly I is an ideal of R. Now if you recall, when we were talking about the radicals, we had shown that an increasing chain of ideals will eventually become an ideal, because the union of those increasing chains will eventually become an ideal, because this will eventually be closed under multiplication by elements of R, because any element to choose out of this union, that element must be residing in some I small I. And if you choose an element, a pair of elements, let's say A and B from this union, then they must be contained in some two distinct ideal, let's say A and B from the chain. But since there is an inclusion, both must belong to either of the chains, both must belong to any one of the two ideals you have. Okay. And then you can justify the fact that this is indeed an ideal. So justify Okay. Yeah, so I is an ideal of R, but R is a PID, right? Since R is a PID, so I must be generated by some element, let's say A. Okay. Therefore, since I is the union of i's, I is equals to 1 to infinity, this implies that A must be in In for some n. Okay, for some n, but these INs are contained in I, right? And I is exactly the ideal generated by A. So if A is contained in In, then the ideal generated by A is a subset of In, while In is contained in I, which is the ideal generated by A. So we have a both sided inclusion. So this means In is exactly equal to I, which this means this chain stabilizes at n. The chain stabilizes at n. Okay. This eventually makes us sure that any element to choose, any non-unit non-zero element to choose, will always get a finite factorization into irreducibles. But what are we eventually left with are, what we are eventually left to discuss is that this factorization must be unique up to associates. Okay. So to show that, what we can do is that we can proceed by induction, but this part is indeed a bit obvious. See, what we are trying to do is that we are trying to show that, suppose the induction hypothesis, or let me write the precise language first, then it will be more clear. The rest of the parts I will not do in details. So we proceed by induction on n, which is the number of irreducible factors, of some factorization of A. Clear? Of some factorization of A. Now if n is equals to 0, then that means that A is a unit. Therefore, if I can write A as some R times S, then this means R will divide A, which means that R divides a unit. So that means R is a unit, which implies R is a unit, right? Clear? So I cannot properly divide A. So which is a contradiction, you might say. I'm assuming this is a proper divisors. So which is a contradiction. Clear? So let n be greater than equals to 1. And the induction hypothesis is obvious that if I talk about a factorization of elements less than n, then I can get uniqueness of the factorization in terms of associates. Okay. I will just prove it for some n factorization. So let A be written as P1 P2 till Pn, which is equals to Q1 Q2 till Qn, right? But now each Pi and Qj are irreducibles. Moreover, we can observe from either side also P1, let's say we start with P1 divides Q1 Q2 till Qm, which implies that P1 must divide Qi for some I, because these are distinct factors, right, for some I. Or whether we are not even concerned about it being distinct factors, we can just say that even if I collect all these same factors and make it into powers, it still holds, right? P1 must divide some Qi, right? But then by reindexing, see, this is just the property of being prime, because since we are talking about irreducibles, we are talking about primes, right? So hence primes, this is what I am talking, hence primes. Now I guess you can observe why this happens, right? So then P1 divides Qi for some I, then by reindexing, let's say P1 divides Q1. So I just bring this Qi to be the first factor in the way we index the second factorization. But if P1 divides Q1 and Q1 is reducible, so Q1 is some U times P1. Therefore, I get the equality P1 P2 till Pn to be U times P1 Q2 till Qm, but then we have a cancellation, we have right cancellation or left cancellation holding because it is an integral domain. So and also it's commutative, so therefrom we can cancel out P1 from either sides to say that P2 till Pn is equals to say Q2 dash Q3 till Qm, where Q2 dash is just U times Q2, but then it follows from induction hypothesis because we have less number of factors than n, so it follows from induction hypothesis, right? So what's basically happening here is that each element on the left, they correspond as associates to each element on the extreme right in the right hand side, but then it will eventually correspond to the ones in the middle because all are in the right hand side we are actually having all the elements to be same up to associates, because see Q2 is becoming an Q2 dash is actually an associate of Q2, right? So eventually all the elements will become unique up to associates, and then it follows from induction hypothesis. This part is quite obvious to observe, right? I guess it's clear. So this is the end of this lecture. In the next lecture I'll try and bring out the concept of, or let me end it with one more thing, which is the concept of a GCD in an unique factorization domain, which we have not discussed yet. Like I said that since we have a well defined concept of a greatest common divisor in a Euclidean domain, we can also define that in case of a unique factorization domain with some changes. Okay. For example, we had seen that in an Euclidean domain I can write the GCD of a pair of elements as a linear combination of those elements in the Euclidean domain, but we cannot do in that in case of any arbitrary unique factorization domain. For example, if you choose the element Zx, then Zx is a unique factorization domain. Okay, you can just simply go by the factorization of polynomials. That's quite a simple case to do here, to deal with here. But if I choose the elements 2 and x from Zx, then the GCD of 2 and x is just 1, which is pretty easily observable. But you cannot write 1 cannot be written as a linear combination of 2 and x in Zx. Clear? But still we can talk about a GCD here, because once we have factors or a well defined finite factorization, then we can surely talk about division in this case, which you have already seen, right? We have the concept of a division defined in case of a unique factorization domain. Hence we can talk about GCD. So how we do this is in the following theorem. Let 0 not equals to a b come from UFD R. Okay. Let a be written as some unit multiple of irreducible, say p1 to the power e1, say p2 to the power e2 till say pn to the power en, where each pi's are distinct irreducibles. Similarly, let b equals to say v times q1 to the power, let's say f1, q2 to the power f2 till say qn to the power fa. Okay. So since the factorizations are unique up to associates, okay, rather let me choose same prime factors, otherwise there is no point of talking about common divisors, right? There is no point of talking about common divisors. So let it be p1 times f1, p2 times f2 till pn times fa. Clear? also these ei fi's are all greater than equal to 0, then d, which can be written as p1 to the power the minimum of the exponents e1 and f1, and I continue this product till pn to the power of the minimum of the exponent en fn is the GCD of a and b. And actually this is a very evident proof, or a very evident observation in fact, because let C divide A and C divide B. Okay. Now the common existence of the common factor is evident because we have chosen the same prime, the same prime factor, so the same irreducible factor. So there obviously exists a common divisor, but to show that this itself is the greatest common divisor in this way, so let C be dividing A and C be dividing B. So we are talking about a common factor C. Then suppose C is say q1 to the power say g1 till say qm to the power gm, where each qi is a reducibles, where each qi are irreducibles. Now qi divides C for all I, so we can just assume to be for some I, and C divides A and B, which eventually means that qi divides A and B for all I. But this eventually means that qi divides pj for some j, right? Therefore this qi's must be some power of or rather these qi's, if they divide pj, these pj's are irreducibles, right? These pj's are irreducibles. Therefore or I can in fact say that qi divides pj to the power some alpha j, which will eventually also mean that qi will divide pj, right? But the thing to observe here is that the exponent of qi cannot exceed minimum of fj and ej, because the exponent of pj in A is ej and the exponent of pj in B is fj. So if the exponent of qi, suppose fj is less than ej, suppose fj is less than ej, so if the exponent of qi is greater than fj, then qi will divide, or qi to the power that exponent will divide pj to the power ej, that is the factor considering qi in terms of C will divide A, will divide the corresponding part of A, which comprises of the factor pj, but it won't divide that part of B, and eventually it won't divide any other part, because we have fixed the case that qi will divide pj for some j. So in order to divide the factor of pj in both A and B, the exponent of qi cannot be greater than the minimum of fj and ej. So since we are talking about a greatest common factor, the maximum exponent qi can precisely comprise of is the minimum of fj and ej. So indeed this basically means, so if we say that D is exactly this structure, then this typically means that C must divide D. That is the end of the proof, right? Clear? Okay. Also we have eventually shown that a unique factorization domain is not a Bezout domain, that is the Bezout lemma does not hold. Okay, but the concept of GCD is well defined here. Okay, so let this lecture be up till this much. In the next lecture I will be trying to discuss about polynomial rings. Okay, so meet you guys in the next lecture.